Hi, so welcome to this lecture again. And in the last lecture, we have derived the equation for bar element. So I'm just rewriting that equation once. So we have basically a cantilever bar element, and we were saying like we have a distributive load which is increasing in this way. So if we say the load was qx, distributed load or qx per unit length, and we got a equation. If we suppose this is the equation, the L length, and we have bar, and so for this particular case of bar element, we can write that bar element here. So we got a equation of EA del 2 u y del x2 plus qx equals to 0. Okay, so this basically is the load acting per unit length. Let's suppose it's we can represent it at rho. So our equation is like E A del 2 u by del x2 plus rho equals to 0. So this was the equation that we derived in our last lecture. So today we'll see how we can write that equation in like general equation to convert it in stiffness and load matrix and all. So we'll do that in today's lecture. So basically there are certain approach, like we have relay Ritz method, we have Galerkin approach, we have different other approach. So generally in this lecture we'll follow Galerkin approach. So what basically Galerkin approach is do. So I'm just writing this Galerkin approach, Galerkin method. So here basically what we are saying is we are saying our like shape function, like weight function is same as shape function, same as our like the function that we are assuming, shape function. Okay, now so basically as we have studied in our initial lectures of FEA, in our courses, like we represent a residue. Okay, a residue R, it will be like we for residue we can represent as for this particular bar equation we just write the whole left hand term of that particular equation. So it will be R equals to EA del 2u by del x2 plus rho. This is our residue. So from that energy equation we can write this as integration of R times Ni dx. This is our weighted function and this is our residue. It's the whole integral will gives us to be 0. This is the basic funda for this. Now put the values, put the basically equations here. What we'll get? We have our equation as EA del 2u by del x2 plus rho. This is our equation and we are multiplying it with shape function and integrating with dx. Now our bar element is from like 0 to L. Okay, so its boundary is from 0 to L. So it will comes to be 0. Okay, now what we can do, we can just multiply, like we can just multiply this Ni and remove that, they make it two separate terms basically. So we can again rewrite it and it will be like 0 to L EA T2u by dx2, it will be Ni dx. plus integration from 0 to L rho ni dx. Okay, and we can put equals to here, and we can put minus sign here. Let's suppose this equation is 1. Okay, let's suppose this is equation 1. We can put it in square box. Now if you see here, the left hand side, focus on the left hand side part, this part. Okay, so we basically try to make it in first order. Basically right now it is in second order, so we'll try to make it in first order. So how we will do that? That we'll do by conducting the integration by part on this left hand side. So what is our basic funda for this integration? We can write it as, like, if we have term like 0 to L limit, and we'll put it del EA, okay, times del U by del X, and okay, now we can get here like this, and this will be Ni. Okay, now this whole term we have, okay, we can write it as 0 to L EA del U by del X del Ni by del X plus 0 to L EA del 2U by del X to Ni, and whole as, or we can put dx here, directly dx here, dx, and this will also be dx. Got it? Now if we this is nothing but the integration by part. If you see thoroughly, if you see, this is integration by part. And one thing here you can notice, like, this section is our right hand section only. Okay, if you see, this is right section only. So we can rewrite this equation, this below equation. Let's suppose this equation is A. So we can rewrite this A equation. Rewrite equation A as 0 to L. We will get EA del 2U by del X to Ni dx equals to, we will get this term. I'm just copying it here. I'm just copying it and pasting it here only. I will paste it here. Okay, and plus same thing I will do here also. I will copy this term also. I will put copy, and I will do it here, and it will took minus sign here. Okay, so this in this way we can write. Okay, now we can perform integration here. So what we will get? We will get basically in right hand side, what we will get? We will get EA del U by del X Ni, and we'll put its limit. We'll put its limit from 0 to L minus, it will be same. Okay, we can write it like it is only. So it will be del U by del X, and it will be del Ni by del X times dx. Okay. Okay, so this much term will get for our this left hand side. Left hand side I also can write here 0 to L EA del 2U by del X to Ni times dx. Okay, this, if you see from equation 1, this is the left hand side, and from the left hand side we can write this whole term as this. Okay, like this. So what next thing we'll do? We will put this in the equation 1 and we'll write equation 1 once again. Put this part, put it in equation 1. So let's see what we'll get. So this will be in right hand term, and the final thing what we'll get basically, okay, it will be like okay, let me write it. So I will just copy this section, copy and paste here, and then what I will do is I will put equals to, and I will take right hand side of this equation. So this is basically, okay, copy, and we'll put it here. Okay, so this is the equation we'll get. Now after rearranging, we can again write this equation. How we can write? So if we see, if the load is concentrated at nodes, so if we see here, this is basically what this thing, okay, maybe. So here if you see this whole term, is basically denoting the concentrated load at nodes, is for in nodes basically. So since net load from 0 to L will be 0, so this whole term will term as 0. Okay, so we will left with our equation to be 0 to L EA del 2U by del X del N by del Ni by del X times dx equals to 0 to L rho Ni dx. Okay, so we'll get this equation. Now here if you see Ni is basically shape function. As I told earlier, it is shape function. Okay, it is shape function. Now what is this shape function is basically? So okay, let's see this. So if we have let's suppose this is our bar element. Okay, and we have node here, node here. Okay, so this I am saying x equals to x1, this I am saying x equals to x2, and I can draw like coordinate system if I'll see here. Okay, I'm saying this is x direction, same way I'm saying this is u basically. Okay, u is basically displacement in x direction. I'm just plotting the graph. Okay, if I'm saying like what I'm trying to show here, basically if I'm saying let's point x1, at point x1 the node is having some displacement, let's suppose with some magnitude. Okay, and at this point we have some its own displacement, let's suppose some point. So there will be a curve that will show the displacement throughout the bar. So we will write a general equation here, UE equals to a naught plus a1x. Okay, as of now I am writing a general displacement equation along this bar. Okay, so if we'll put the value of x, x1, x2 and any other value in between that, we will get the displacement at that particular point. Okay, now what we'll try to do is we'll try to denote this displacement in terms of nodal displacement. So if we see nodal displacement, let's suppose as x1 we have some constant displacement, and in the same way we have at x2 we have some constant value of the displacement. Okay, so we want to try, so we basically need, we need to express the displacement function, in terms of in terms of u1 and u2. What these u1 and u2? u1 is basically displacement at x1 and u2 is basically displacement at x2. Got it? So how we will get? So before, what we are saying is, in our problem it will be given basically like at x1 we have displacement u1. Okay, so we can write as ue x1 equals to u1, and at x2 we'll have ue x2 as u2. Okay, so now we'll put put these x1 and x2 in the equation. We'll get two equations basically. So we'll get u1 equals to a naught plus a1 x1, and u2 equals to a naught plus a1 x2. Now from both the equation we can find the coefficients. Okay, from both these equations we will get coefficient, and after calculation, like after these form like two equations solving, we'll get a naught as some u2 x1 minus u1 x2 divided by l. L is basically length of the bar. Okay, at x2 is basically some length, and l is basically, we can write l as l, we can denote here l equals to x2 minus x1. Okay, got it, na? Yes. So in the same way we can get from this equation only, we'll get a1 as u2 minus u1 divided by l. Now we have a naught and a1. Okay, so we have a naught and a1, and what we'll do is we'll basically put these a naught and a1 in this equation, in this displacement equation. Okay, let me take this basically. Okay, I'm copying this equation here in general form, and I'm putting the values of a naught and a1 here. So what I will get ue, so ue I will get as some I am just directly putting comma in this, I'm just putting it here only. Okay, again we have this one also a1, I'm putting it here. Okay, so we have a naught, this is our a naught, plus this is a1 times x. Okay, so this will be the general displacement that we are assuming that can be written as in this way. So after since what was our target? Our target was to convert this displacement equation, general displacement equation, in terms of nodal displacement. Okay, so we can rearrange this equation and we'll get the equation like, after rearranging we'll get our equation like x2 minus x divided by l u1 nodal displacement at x1 plus x minus x1 divided by l at u2. Now we got our displacement equation like this. Okay, in terms of nodal, in terms of our nodal in terms of our nodal displacement. Okay, I can write it here as nodal displacements. Okay, nodal displacement, this u1 and u2. Okay, so here what we got is, we got some something here. What we got, I can highlight this. One is this and one is this. So basically we can write n1 as x2 minus x divided by l, and 2 as x minus x1 divided by l. So by writing this, now we can write our equation ue as n1 u1 plus n2 u2. We got our displacement equation in terms of nodal displacement and shape function. Here these n1 and n2 are nothing but our shape functions. Okay, what are these shape functions? Okay, shape functions. So we got our shape functions n1 and n2. So let's visualize like how n1 and n2 will vary. So I have made one figure here. So let me copy this, and I will put it here. So if I'm saying I have shape functions n1 and n2, so what is the special thing about these shape functions? So the special thing about this shape function is, so for n1 it will be having a value of 1 at node 1 and 0 at node 2. So if I am saying this is n1, it is having 1 at node 1 and 0 at node 2. Okay, this is n1 u1. Okay, this shape function is n1 u1. I can write it like this. And we have another shape function, that is n2. n2 having maximum value at node 2 and it will be having 0 value at node 1. So we can write like this. So this line we can say as n2 u2, and this linear line from this point to this point, it is called as n1 un. So these are the shape functions. So after, when we combine these two shape functions, like when we will combine these two lines, these two black dotted lines, we will get this blue line. Okay, we'll get this blue line. I hope it is clear. Now I hope up to this it is clear. So let's again put that main equation into picture. I'm just copying this main equation from here. I'm just copying this equation from here. Okay, so basically up to this we are getting this like displacement equation, right? We are getting this displacement equation in terms of shape function and nodal displacement. Now we have to find these like double derivative of u. Okay, double derivative of u, and this ni we have to get, and then we have to put here and here. Okay, then again we will see what will happen. So let's take it as it is, and we'll perform some basic things. So basically we need del 2u by del x 2. Okay, so before that, sorry, I think I made a mistake here. So basically since we have already make it in first order, so it will be 1 only. Okay, so it will be y, sorry, what I'm doing, yeah, it will be del u. So I think initially I have made some mistake. Yeah, here if you see here, this 2 will not be here because we already made it in linear form. Okay, so it is clear, right? Okay, now we have these two things. Okay, we have our ue as n1 u1 plus n2 u2. Okay, now we can find here like del u by del x. What we'll get here? See, if you see n1 from here, it is a function of x, n2 is also function of x. Okay, so we can write, and u1 and u2 are constant. Okay, so we have to differentiate this n1 and n2 only if I'm with respect to x. So what we'll get here? We will get here as u1 del n1 by del x plus u2 del n2 by del x. Okay, in other term we can arrange it in matrix form. What we can write is del u by del x del v, sorry, what I am doing, man. So here we can write either del n1 by del x del n2 by del x, and this is basically matrix notation, del u by del x. So if we see here, this is constant term and this is variable kind of. See, if we have linear, then it will again it will come as constant. Okay, so up to this we have del u by del u by del x we got. Okay, now what we'll do next is we will put the del u by del x in this above equation. So let's see what we'll get. Okay, so it will be 0 to L times EA times del u. So del u we can write as del n1 by del x del n2 by del x, and it will be, see, we have okay, I can just write as of now, then we'll do something. So u1 u2. Okay, and here we have del ni by del x dx. Okay, equals to 0 to 1 rho ni dx. Okay, up to this it is clear, right? Now as I told here that this u1 u2 these two are constant, so we can remove these two out from the integration. So what we'll get here, we'll get basically paste it here, and what I will do is I will remove this and I will write here del ni by del x dx. I hope everyone is getting why I am removing out of this integration these two things, because they are constant. Okay, now we can write this equation as it is, 0 to L rho ni dx. Okay, so we have this equation. Okay, we have this equation. So we have to integrate this term up to this, we'll get something, and we have to integrate this term, we'll get something. Okay, so from here we can say that this is our stiffness matrix. And this is our nodal force. Got it, right? Now if I will say total how many equations we'll get here, total how many equations from this, if you clearly observe here, I am writing as ni. Okay, ni. So it means we have total how many n's? We have n1 and n2, right? So we will get two equations. Okay, how many equations? Two equations. Okay, let me write those two equations. Okay, so first of all we have n1. So we have n1 equals to how much? Okay, let me copy it from here only. I will copy both. I will copy from here and I will put it here only. Okay, so from here we will get del n1 by del x, it will be minus 1 by L, and this value will get del n2 by del x, and this will get 1 by L. Okay, now we'll get one for first equation we will put I equals to 1 and we will get one equation. So in place of del n1 by del x we will put minus 1 by L. So let me write okay in this way, I will write both equations. Okay, I'm just copying it here. I'll paste it here. So for the first equation, what will happen? Here it will come as 1, right? So here it will come as 1. So what I am doing is I am putting the value of del n1 by del n1 by del x here. It will be minus 1 by l. So I am directly writing here as minus 1 by l. Okay, in the same way for the next there will be one more equation for n2 also. So I will do the same thing here, and again we'll get here as here at this location we'll get as del n2 by del x. So I will put this value 1 by l here. So I will do 1 by l here. Got it, right? And one more observation we'll get, since this is constant, so it will also get out from this integration. Okay, or yeah, it will get out from this integration, and we can write it as okay, we can write it as so this is our stiffness matrix. So as of now, let's focus on stiffness matrix only. Just focus on stiffness matrix only. As of now, I am not taking these terms. Just focus on stiffness matrix, and after working on the stiffness matrix, we will do for that nodal force also. So let's focus here only. So let's suppose this is equation 1. Sorry, let's suppose this is equation maybe 3, and this will be equation 4. Again, what we'll do is we can combine these two equations, make it in matrix form in a smart way. So how we can write that I will show you here. And so what we can do is we can make our integration like this only, and we have EA common here. If you see here, it is like L is constant, right? So we can take common, like we can put that L here, and what we can do is we can put these del n1 by del x, these values here, value here also we can put L. Okay, here also we can put L. Got it, right? So if you see one more thing, here I can directly put del n1 by del nx, del n2 by del x from here. So once again let me write, so what we'll get from here basically, let me write like that only. So here for from first equation we will get minus 1 by l, and it will be 1 by l. Okay, and here it will be minus 1 by l. So I'm just, as of now, I'm just removing this l from here, and here we are getting del x. Okay, here we have u1, u2. Okay, now I can rearrange this. For this, I'm working for this for from equation. We can write equation. We can basically write equation, right? We can write equation 3 as below. Okay, now after rearrange these terms, we will get something like this: EA by L square, and here we will get 1, it will be minus 1, it is dx u1 u2. Here is our integration from 0 to L. This is for first equation, means this is for our, let's suppose this is 3 dash equation. Okay, now for equation 4 we can write as, now equation 4, this is our equation 4. So we'll write it like the same way only. It will be 0 to L, it will be EA, and after putting del n1 by del x, del n2 by del x, we'll get it as EA by L square, and in that inside we'll get as minus 1, 1, and it will be dx, and outside of the integration we'll get u1 u2. Okay, we'll get u1 and u2. So up to this we have these two equations. Let's suppose it is 4 dash. Okay, let's suppose this equation is 4 dash. So what other things we can write? So for the whole complete linear bar, so for the linear bar, the stiffness matrix can be written as, what we can do, we can combine these 3 and 4 equations. Okay, how we can represent it in matrix form? We will get it as 0 to L, since this EA by L square is common in both, and we can use everything else is common except this matrix, so we can write it as combine these two matrix, and we'll get 1 minus 1 minus 1 1. It will be dx. Okay, it will be dx, and it will be u1 by u2. Okay, one more thing I want to tell you. See, this is our like stiffness part. Okay, this is constant part, this is outside that what we can do, our stiffness matrix, right? So we can remove this u1 as of now. This is outside the stiffness matrix, right? Not required, not required. Here also it is not required, here also it is not required. Now we have this constant matrix, we have this constant term. Now we can easily integrate this term, so we will get it as ea l square matrix 1 minus 1 minus 1 1, and it will be x limit from 0 to L, so we'll get as L, so 1 L will be cancelled. So stiffness matrix, so we'll get stiffness matrix as ea by L 1 minus 1 minus 1 1. Okay, so this is our local stiffness matrix for linear bar element. Okay, for linear bar element. Now linear bar element means we are considering our shape functions as linear. As you can see from here, if you see, it is the function of x linearly. Okay, so these are linear shape functions. Okay, in the further we'll talk about quadratic shape functions also. So if we consider our shape functions to be linear, then we'll get our stiffness matrix like this. Now let's suppose we are assuming our shape functions to be quadratic. So let's go for shape functions quadratic. So what we mean by this quadratic basically? So initially we have in the last one we have observed, like we are getting one straight line, right? A linear straight line from u1 to u2. Okay, so if we are saying our shape functions to be quadratic, so how it will be like, let's suppose that same beam we are, like, sorry, bar, same bar we are saying we are taking here, and I'm just trying to draw this x-axis, and I'm saying this is the magnitude of this u. Okay, displacement. Okay, I'm saying we have one node here, we have one node here. Okay, I'm saying it is quadratic. So what we are doing is we are taking 3 nodes, we are making one more, we are adding one more node in between the same element. We have one element having 3 nodes. Okay, so we are making it quadratic. So we have some displacement at this node here, we have some displacement at this node here, and we have some displacement for this node here. If we draw this, we will get a curved line. Okay, let's suppose it is here, something like this, u1 u2 u3. Okay, now this is x equals to x1, I'm assuming, and it is x equals to x3. And at mid only I am assuming this, so it will be x1 plus x3 divided by 2. Okay, at mid. Now for this, what will be the general formula for that displacement in this quadratic one? So we can write it as u equals to a naught plus a1x plus a2x square. If you see here, you will get a second order, like second degree of this polynomial. Okay, 2-degree polynomial for this particular displacement equation. Okay, so we have u as a naught plus a1x plus a2x. Okay, now again, as earlier we have done, like we have to convert this u in terms of nodal displacements. Nodal displacement means u1, u2, u3. Okay, with some shape functions. Okay, now what we'll do is we'll put it like at u1 we what we'll get, like u1 u, basically it will be u x1 equals to a naught plus a1 x1 plus a2 x1 square equals to u1. Okay, in the same way u x2, it will be a naught plus a1 x2 plus a3 x3 square. Sorry, this will be x2 only, this will be x2, so it will be u2. In the same way x2, if I am saying x2 is basically x1 plus x3 divided by 2. Okay, so okay, let me write in this way only, it will be more clear. So it will be x1 plus x3 divided by 2 plus a2 x1 plus x3 divided by 2 whole square equals to u2. Okay, now u x3 we can write, it is very easy basically. If you can observe, I'm doing nothing, I'm just putting the values and all, means these in terms of x plus x and x1 x2 x3. So it will be x3, and a2 it will be x3 square. Okay, it is u3. Now we have these three equations, and from these three equations we can find a naught. We have three unknowns and three equations for a1, a naught, and a1, a2. So from these three equations, after solving, we will get our a naught, a1, and a2. Okay, so what we'll do, what we'll do basically, so we will then again put these a1, a2, and a3 in this equation. Okay, in this general equation, and we will write our equation in terms of u1, u2, and u3. Okay, so we'll get our equation something like n1 u1 plus n2 u2 plus n3 u3, like this. Okay, we have our displacement in terms of u1, u2, u3 and shape functions. Okay, now shape functions will be coefficients of u1, u2, and u3. As I have as I have solved here, we got some n1 and n2 here, like not here, I have derived somewhere, right here, where I have written, yes, here, this and this. In the same way, coefficient, these are coefficient of u1 and u2. So in the same way, for this quadratic one, we will get our n1, n2, and n3. I am directly writing what we'll get. It is very easy. We can again just rewrite these equation and we can get these n1 and 2. I'm just directly writing what we will get here. Okay, so let me change the color. So from here we'll get n1 as x3 minus x, x1 minus 2x plus x3 divided by L square. Okay, n2 will get as 4 x1 minus x minus x3 divided by L square. Okay, in the same way we'll get n3 as x1 minus x x1 minus 2x. See, I'm not writing anything magically, okay? These two I already have written earlier, so I'm just writing from there only. We can easily get these terms from these three questions only, okay? So don't worry about this. If you have any doubt, just try to just rearrange the questions and get the values of n1, n2 and n3. Basically they are the coefficient. Okay, now up to this we have the shape functions for quadratic. Okay, means we have n1 and n2 and n3, these are quadratic shape functions. Okay, so we have quadratic shape function and we have initially we have linear. No, now we'll see how that stiffness matrix will get in terms of this quadratic one. Let's see. Okay, first of all, before going to that stiffness matrix, we'll see how this n1, n2 and n3 will be. So as I shown you here, like let me copy this first. As I shown you here, yeah, as I shown you here, if I'm saying our n1, n1 will give 1 at node 1. Okay, so I can say like our n1 is this only, this, and it will be 0 at u2 and u3. Okay, it will be 0 at u2 and u3. Now this line denotes our n1 u1. Now n2 u2 will be, if you see n2 will be 0 at x1, it will be 0 at x1 and x3, it will be maximum at u2. So we can write, okay, let me change this color for u2. Okay, let me make it as red. So n2 u2 will be, shape function will be like this. So this is denoting n2 u2. Now if we carefully see n3 is basically maximum at 3 and rest of there it will be 0. So I can put this as 0. Again it is 0 here. So this is n3 u3. Okay, this is and after combining these three shape functions, these n1 u1, n2 u2 and n3 u3 curves, we will get the main curve, this black line, u1 to u2 to u2 to u3. Okay, I hope this idea of shape function is clear up to this point. And next we'll move to stiffness matrix for this particular case, and this case is stiffness matrix for quadratic bar elements. Okay, so up to this it is clear, right? Now we'll see the stiffness matrix for this case. Stiffness matrix. Okay, so we know that the stiffness term, what was that stiffness term? General stiffness term we have 0 to L EA del U by del X del Ni by del X dx. Okay, so this is our stiffness term. Got it? Stiffness term. Now we need del U by del X, and as we see we have this U. Okay, we have this U, we have n1, n2, n3. Okay, now I can erase this and yeah. So from here we can write del U by del X. It will be u1 del nn by del X plus u2 del n2 by del X plus u3 del n3 by del x. Now here also we can write in the same way. Our matrix will be del n by del x, del n2 by del x, del n3 by del x, and our nodal displacements u1, u2, u3. This is our del u by del x. Now we have ni. Our ni will be how we can write our ni? Ni can be written as, like, once we will take 1, then again I will be 2, again I will be 3. So in the same way we will have 3 equations. Okay, how many equations will have? 3 equations. So first we will write that stiffness matrix as, we have integration from 0 to L. We have EA. We can put the terms for del u by del x, and it is basically del n1 by del x, del n2 by del x, del n3 by del x, and we have this term u1, u2, u3, u1, u2, u3, and then we have this shape function derivative term dx. Okay, so if we see here, let's calculate this, since we have n1, n2, n3. Okay, let me, where is that n1, n2, n3 I have put it? Okay, here. Let me take these terms, copy here, and I am just, in order to take reference, I am putting it here. Okay, here only. Okay, I'm making it a little bit small. I'm saying these are our n1 and 2. Okay, now so for del n by del x 1. Okay, so if we integrate del n1 by del x, what we will get? We will get, so one more thing we can write it here as, like, since we are going from, like, we have 3 nodes, right? 1, x1, let's suppose x1 we are assuming to be 0, and x3 we are saying length L. So, and it will be x2, and so in that way it will be L by 2. Okay, midterm, this will be L by 2. Got it? This will be L by 2. Now we can write our del n1 by del x by under these conditions as, after differentiating with respect to x, we will get 4x minus 3L divided by L square, and del n2 by del x we will get as 4 times L minus 2x divided by L square, and del n3 by del x will get as minus L minus 4x divided by some L square. Okay, so we have our derivatives of n1, n2 and n3 with respect to x. Now what we will do, we will put these in this equation. Let's suppose this is our equation. Okay, so what we'll do here, so we'll just put del n1, n2, n3 in these equations. So we can write our equation as integration 0 to L. If you see here, EA is common in all three, and this L square is common. So I am taking it as EA by L square. I am putting it in matrix. We'll get is 4x minus 3L. Next will be 4L minus 2x 4x minus L. Okay, and here basically we have Ni, right? Here if you see we have Ni. Where is the, yeah, this Ni. So it means I from 1 to 3, 1 2 3. Okay, 1 2 and 3. So first we will get N1 by del x and we will write dx. Okay, so if you see this now, this is constant term, it will go right side, and only this much of the term, like this much of the term will be our stiffness matrix. Okay, stiffness matrix, because this is constant, this is outside. Now as I described like earlier also, so we have our one equation. So let's suppose this equation comes as P equation. Okay, and I will put this n1 we have already given, so we'll put n1 later. So in the same way we'll get two more equations for n2 and n3. So I'm just directly copying this, I'm pasting it here, and I'm making here as 2. Okay, I'm making here as 2. So this equation I'm saying Q. In the same way I'm again copying it and I'm making it 3. I'm saying this equation is R. Now what we'll do, again we'll put this value, let me highlight it, this value, this value, and this value again we have to put. Okay, so after doing this, see, this whole term is constant. Okay, and this is variable, we'll put this value, and these are the variables. So this is simple, means if you see integration is simple, that x, if you put x square, some polynomial will come 3 times, it will come in the same way 1 2 3, here is it will come. So it will be a little lengthy, so I'm directly writing the integration. Finally, after doing the integration for the above equations, we will write the whole 3 equations in one, and we can write it as ke 2b, it will be ea by L square, and we'll get a 3 cross 3 matrix and some numbers will come. Okay, all these things will come when we solve these 3 equations. Okay, don't worry about this, just understand the concept. Okay, so this will get our stiffness matrix for quadratic elements. So for linear elements we got our stiffness matrix. Here I explained here, this is for linear element and this is for quadratic, that I just now I explained. I think it is clear. So for both linear and quadratic we have this stiffness matrix. Now as I shown you guys earlier, like in our main equation we have stiffness term as well as that nodal force term. Okay, let me show that main equation. Yeah, here if I, what I will do is I will just taking this thing, I'm just copying it. Yes, here. So here if you see, this is stiffness term and this is our nodal force term. Got it now? Yes. So we have done for linear and quadratic, we have done with this stiffness part as of now, and we'll see to represent our nodal force. So we'll look into this section for nodal force. Okay, we can do one thing, we can just explore more this stiffness matrix, and then we will start with that thing. Okay, I think the next, as of now, this stiffness term, I think that is fine, and in the next lecture I will explain, like we'll have different, see in this case we have only 1D element, 1D linear element and quadratic element we have shown, right? So up to this, how to calculate the stiffness matrix for 2D elements like triangular elements and like chord elements we can say. So in this way we'll get some idea about our triangular elements or some other 2D elements, and then we'll see how we can find the stiffness matrix for this. Okay, then we'll go for further things. So I think for this lecture that's it, and we will see further calculation and further derivations in the next lecture. So tata, bye bye, thank you for your time.